All right, I'm going to start. So there's a chance we'll get done early today because I started a little bit late last time because of a technical error. So, oh darn, end Friday afternoon a little bit early. We'll see. We'll see if that really happens. So I have a couple technical logistic announcements. MP4's extra credit is due tonight. Let's see. There is an MP3 solution party on Sunday. So MP3 solution party. Sunday, that's the 5th, right? 5 p.m. in Siebel 1404. Nathan Walters is going to be doing it. Nathan Walters and Mike Perez are going to be doing it, I believe. It'll be great. It'll be really good. So the intention is for them to give you kind of an idealized view of the solution to MP3 in a kind of think aloud way. So to kind of help you reconcile the agony that you went through in designing your solution with the oversimplified view that you're going to get on Sunday. So we want you to see this idealized view, so that you can move toward it ideally. Yeah, you'll come out of there going, "Whoa, that's not so hard, darn." Except that it is. It was hard for them too, let me tell you. Yeah, Neil?
So, will we ask about
Ask about questions about the exam that you already had, the exam that you already had. We hadn't talked about that. Was this going to be a solution party or an exam review party? Okay. So we haven't talked about exam 3, like doing that kind of idealized view of exam 3. Why don't you post that to the piazza? Because I want to ask Nathan if he wants to do that. But, I mean, it seems kind of okay to me since they're pretty tightly coupled. So post that question to the piazza. Let's see. I'll announce this more, but for the next exam, I anticipate that the content will be a little bit from MP4 and a little bit from lab trees. Like I think those lab tree little puzzles that you had to solve are about almost exactly the right scope for an exam setting. So I'll talk to Wade about that and make sure he gets that word, but that's my intention, at least for our next exam. That's what I'm thinking it'll look like. Okay. Oh, the other thing I wanted to tell you was I thought of you collectively. Today, I usually read the tech section of the New York Times, and today, I don't remember whether it was in the business section or the tech section. They're right beside each other on the homepage. Today there was an article on 3D geographic mapping for autonomous vehicles, and it opened, like I had never thought about this before. So I'm interested in autonomous vehicles. I don't claim any expertise, but I am so committed to the idea of a world filled with autonomous vehicles that we don't even let our own kids get their driver's licenses, okay? That we believe that by the time it's important for them to drive, there will be autonomous vehicles. So that's it. But in today's New York Times, there was an article that made me think about it from a slightly different perspective, and that was the technology around creating 3D maps to be used collectively by the people who are creating the autonomous vehicles. So this was like, for me, it was sort of like seeing Google Maps, the 2D version, in its infancy. Right? Like if you saw Google Maps for the first time, I was realizing, oh my gosh, autonomous vehicles need a uniform standard of 3D interpretation. And what does that look like? Moreover, it has to be real time, right? Like it has to be, the maps have to be updated all the time. And what are the technical approaches to solving that problem? It's mind-blowing how interesting it is. Moreover, that same technology can be used to map coral reefs, to look at changes in the environment from lots of different levels. So I sort of felt like my technical world and interest set had changed slightly today. Yeah? Oh, so yeah, so the autonomous vehicles issue, the comment is that there are huge security issues, that like if your enemy was in an autonomous vehicle, could you like steal control of it or, you know, whatever. So yeah, so the security issues are huge as well. Like, oh my gosh, what a fun time to be alive. All right, so there's that. So I guess I'll write it down. New York Times 3D mapping article. 3D mapping. It's light, it's cute, but it talked about the companies that are doing it and some of the issues involved. All right, my life changed in another way last night. Raise your hand if you know where this came from, or if you've seen it before. Where did it come from? So, up until last night, I didn't know about UIUC memes. Now I do. I feel like I have scratched the underbelly of the internet and I came away going, ew, I don't know. I didn't join, so you have your own little playground if you like. But I did stay long enough to find this perfect contribution to today's lecture. Oh. All right, so yeah, we're going to hold with the classic notion of perfection here. Yeah, you have a comment? Oh, I screwed that up. I'm sorry. I had a typo in the link. So they will be as soon as I get back to my desk, but they aren't yet. Sorry about that. Yeah, so the online slides, it was a typo on my part. You make a meme out of a typo, I don't know. Okay, so sorry about that. Okay, so we're going to stick to the classic notion of perfection here in the context of a combinatorial structure that we refer to as a tree. So this is not true. Only this one is perfect. And we've seen a recursive definition of it that observes that if we parameterize this thing by its height, what's the height of this one? The height of this one is 3 is correct. If you wanted to say 4, you were probably counting vertices instead of edges. Height is a distance. You count edges, a distance. Okay, so the height is 3. We characterize perfection by observing that a perfect tree of height h is either empty or it's a perfect tree of height h minus 1 on the left, perfect tree of height h minus 1 on the right, and together with a root. Okay. Any question about that? So this one is perfect. Very quickly, draw a tree which is not perfect that has 5 vertices. Race you. 1, 2, 3, 4. 1, 2, 3, 4, 5. There. 1, 2, 3, 4, 5. That one's not perfect at all. Okay, this one isn't. Okay, those are not perfect trees. Any question about what perfect trees look like? All right, I've got some questions for you. We talked about height, and we talked about it as a distance from the root to a leaf. I want to know, what's the height of that tree right there, this one? This tree. What tree is that? Yeah? No, not that tree. Not that tree. This tree, right here, I'm touching it. Yeah, I'm asking about the height of a non-tree, right? The height of an empty tree. So the height of an empty tree, and I'm going to write it like this. This is just a reminder that because we define heights by path length, we don't have a way of defining this mathematically because we don't have any paths, right? We don't have any paths to measure. This is the path length in the absence of a path, which means we can define it to be anything we like. It's a vacuous scenario. We can define it to be anything we like. It turns out to be nice mathematically and elegant structurally if we define it to be -1. Okay, so the height of an empty tree is -1. Okay, I have one more little talking point to make in the context of this slide. And that talking point is to ask you how many vertices there are in a perfect tree of height h. How many vertices in perfect tree of height h? We oftentimes will write the number of vertices as the magnitude of, the size of. These vertical bars, kind of like absolute value, but vertical bars mean size of. Should we talk about a way of addressing this problem? One way of addressing this problem is to look at this thing row by row. What do you observe about the pattern of the number of vertices in each row, each level here? We'll talk about level in just a second. It's the sum from k equals 0 up to the height of, how many do we have at each one of those levels? 2 to the k, good. All right, does it bug you that I wrote that down as a sum? It doesn't? There's a closed form. What's the closed form for that sum? There we go. All right. So the number of trees, the number of vertices in a perfect tree of height h is 2 to the height minus 1. 2 to the height plus 1 minus 1. Okay? Any question about that? And that will be useful to us later on. So I'm kind of going to bring it up every so often. Okay. So this ends our discussion of a perfect tree. Last time I gave you a definition of a full tree. So now we've got these two kind of similar vocabulary words, full tree, perfect tree. It's sort of, how do you feel after dinner? Well, I feel full. Well, I feel perfect. The other way you might feel is complete. Okay? I don't know if you feel complete after dinner. All right, so here's the thing. A complete tree is yet another one of these superlative trees. It's almost like a perfect tree. In fact, in some mathematical contexts, the perfect trees and complete trees are the same thing, but not for the purposes of this class and not for most computer science theoretical discussions. Now, so what is a complete tree then? Well, it's a perfect tree where you've erased or removed or gotten rid of, or maybe they never even existed at all, some of the vertices. The vertices that you might have gotten rid of or that might not exist from your perfect tree are the ones on the right on the bottom row. Oh my gosh. Okay? Yes, that's it. Any question about that? Well, I don't like that description at all. So I went to the National Institute for Science and Technology, Standards and Technology, NIST. I went to NIST, which is where all these structures are officially defined, nist.gov, right? Standards and Technology, National Institute for Standards and Technology, I think. And I said, okay, what's the definition of a complete binary tree? And what I got was only a little bit better. It says, first of all, you have to know what a level is. So a level is a distance from root. So the set of vertices on level 0 is the set of vertices distance 0 from the root. The set of vertices at level 1 is the set of vertices distance 1 from the root. Level 2, distance 2 from the root. Level 3, distance 3 from the root. Okay, so that's what a level is. It's a measure of distance from the root. Different than height. It's different from height. Okay, for any level from 0 to the second to last one, level K has 2 to the K nodes. It has all of the possible nodes in a binary tree. Okay, so down to here, we've got all possible. On the last level, all the nodes that exist are, I kid you not, pushed to the left. Heck, that doesn't feel very mathy at all. And yet, that's the official thing. So, for example, I could ask you, if I get rid of O, is it a complete binary tree? No, because there's that gap there, right? All right, any questions about complete binary tree? Is this one? Let me ask you this. I'll ask you a couple of them. Is that a complete binary tree? No, the left part matters, okay? Left is different from right. How about this one? That one? Is that a complete binary tree? Yes, it is. How about that one? No, okay. How about that one? Yes. That one? What do you think about that one? Yes, it is. Okay. All right. Any questions about it? How about this one? No. All right. You get it? All right. So I don't like this definition because it's not a recursive definition, which means I feel like writing code that are functions of complete binary trees would be hard because I don't have a recursive definition. Well, it turns out that there's this nifty little puzzle that exists that turns this definition of a complete tree into a recursive definition. So what I want you to do is just solve this puzzle. The way to solve the puzzle is to recognize, okay, base case, that's easy. But to solve the recursive case, to look at the left subtree and the right subtree and to characterize them in terms of things you know about smaller such trees. Okay? All right, so go ahead and try to solve the puzzle in this way. Okay, so what's a recursive definition of a complete tree? What do those trees look like? What's the one on the left look like? All right, look at the paper of the person sitting next to you. Way too quiet in here, especially for a Friday. Raise your hand if there's pencil mark on that slide at all. Pencil mark on the line, on this corresponding line at all. Nice job. I saw that when I walked past. Good job. Okay. All right, fine. I can't win that one, right? Okay, what kind of tree is that one? Yeah, it's a perfect one. How tall is it relative to H? I know it's height too. But in general, if this tree were much, much, much larger, how tall would it be? 1 less than h, right? And what does this look like? Is it perfect? No. Is it full? No. It's complete. And how tall is it in general? It's 1 less, right? H minus 1. Okay, good. Okay, fine. Anybody get the other case? The other case is easier to see if I get rid of a few of these vertices. If I get rid of a few of these vertices, then the subtrees look more like this and like that. Okay, so what does the left one look like? Is it full? Is it full? The left subtree, is it full? Yes, it is. We'll talk about that in a second. So the left one is complete of height h minus 1, and the right one is, what letter am I going to write? P is correct. And what number am I going to write? 2, good. Okay, so this is one way of characterizing a complete tree. It's recursive. It demands that you have a notion of a perfect tree of height h. But so that means that if you have functions on complete trees, you can deploy your code in this form if you want to. Now, we're going to write functions on complete trees later on that don't demand such craziness, okay? So this is just for the sake of puzzle here. Okay. Is every full tree complete? Yes or no? Yes would be like this. No would be like this. I won't even make you raise your hand today. Every full tree complete, is it? No, it's not. In fact, here's a full tree that is not complete. Oh, look, right there. That one's full and not complete, right? What does full mean? Every node has 0 or 2 children. Okay? Is every complete tree full? No. So this is no. This is no. And for the example of that, point to an example. The original tree, right? The original tree, the original example tree has 1 vertex. So it's not full. All right, how are you doing? Yeah? Yeah? Okay. Yeah, so I guess I want to re-emphasize that we're going to see complete trees later on. I'm going to let you kind of remind me of this discussion at that point. In fact, you're going to want to keep an eye out for an opportunity to represent something as a complete tree. And you can go, yay, yay, now's the moment. All right, so what we've been talking about so far is theory, definitions that characterize the structure of these trees. We've been very far removed from the data that the trees contain. We didn't talk 1 second about what's inside the nodes of each of those pictures, as well as how we implement these trees in memory. Now, most of you have already done the trees lab, so you've already seen how we implement these things in memory, but I'll refresh your memory by saying that we do it kind of like we do linked lists, right? We have a node pointer inside the tree, and every node is a little piece of data together with pointers to subtrees. Finally, we represent a tree completely by holding on to its root. And we trust the fact that if we have the root, we can get everywhere else in the structure that we would like. Let me ask you a couple questions. Does such a structure have a copy constructor? Would you expect this thing to have a copy constructor? What do you think? If we're representing things in memory kind of like that, and we're holding on to it via a root, would you expect a copy constructor? You can do this or this. The answer is this. Yes. Because the way that each of those nodes is created is via a new, right? Anytime we want to add data to this structure, we're going to be creating a new node on the heap. And so, if that's the case, then we're going to need a copy constructor and a destructor and an assignment operator. So these are things that live in dynamic memory. Now, I very casually made reference to the fact that if we insert into them, well, here's the thing. We don't actually have a principled way of deciding where we would put new data in here. If I came up to you and I said, I want to put 52 into that structure, where would you like me to put it? What would you say? My data is 52. I want to put it into that structure. Where should we put it? Yeah? I've got a 52. I want to put it in that structure. There are lots of right places to put it, right? I could put it right here. 52, like this, right? There's absolutely nothing in the discussion that we've had so far that precludes me from doing that. There is no notion of inserting into a particular place yet. So I assert that we can talk about implementation, but we cannot yet talk about the abstract data type. We don't know what they're used for. We don't know the significance of the data they contain, so we can't prescribe an addition or a removal from the structure then yet. So this is not yet, until we're looking at particular kinds of trees that take care of data in a particular way, okay? All right, so we're not ready for a tree ADT yet. We may never have a tree ADT, actually. There is something on this slide that really bothers me, though. I look at this. First of all, I look at this, and I go, oh, that looks just like, what does it look just like? Where have you seen that structure before? Who said list node? Yeah, for a doubly linked list. That's right. Look at that structure is the same as a list node for a doubly linked list, except that we're using it completely differently, right? We're not putting our data in order. The idea of next has a different meaning in this context. All right, fine. Now I look at the way we're intending to use it, and I'm a little bit bothered by all of these extra nulls. Are you bothered by that too? Tons of nulls are there. How many nulls are there in a doubly linked list? So we've used these nodes before. How many nulls were there in a doubly linked list? 2 of them, right? A constant number of them. The previous of the head and the next of the tail, those we both use null. Okay? So a constant number of nulls for a doubly linked list. We certainly weren't bothered by that. What if I told you that there were n squared nulls? How would you feel about that? Where n is the number of data elements. If I said there were n squared nulls, would you be bothered by that? No? How much data do you have? N, right? So I'm going to draw you a little picture to help in the argument. Here's how much data you have. Okay, this is the meat. This is your cash crop. Okay, and here's how many nulls you have. Okay, that's like the infrastructure. That's the additional memory you need to keep track of this little piece right here. Now, memory might be cheap, but it's probably not so cheap that you can spend n squared to maintain your structure. So it would be really bad news if there were n squared nulls, okay? And I'll be happy to tell you there aren't, yay. What if there were logarithmically many nulls? What if the number of nulls was log? Would that be good news or bad news? Would that be okay? Yeah, guess what? It would be fine. In this tree, it would be sort of like we were storing every row as its own linked list. For complete and perfect trees, that's the case. For short trees, it would be kind of like we had a sentinel node in the front of every, or an extra null pointer in the front of every level, something like that, okay? So it's not too much. Now, though, what I want from you is for a tree containing n nodes, how many null pointers are there exactly? How many null pointers are there? Now, what I expect is that you'll sketch some. You'll count what you have here, and then you'll sketch a couple so that you can sort of test your hypothesis. How many do you think there are? A tree of n nodes has how many null pointers? N plus 1, you believe that? Okay. Is that too many? No, n plus 1's okay. It kind of means that we're taking our data and we're insulating it a little bit. Okay, we're making our data a little bit chubbier, but that's okay. Little insulation never hurts. All right, any question about that? So we're willing to put forth that much more memory for our data. All right, so if this is true, if it is true that in the general case, if there are n items in our representation of a binary tree, then there are n plus 1 pointers, then we're happy. That's okay. So if there are n data items in a binary tree, in our representation of, then there are n plus 1 null pointers. So you should not take my word for it. You should not take your neighbor's word for it. You should not take it as proof because you sketched 5 trees. You should prove this. Now, we're making an argument on a binary tree. We're making an argument on a binary tree. Binary trees are recursive. It begs us to prove this theorem by induction. So this is exactly the setup where we're going to be able to solve this problem by induction. Okay, you ready? Now, I'm going to do a lot more talking than I like to do. It's going to be think aloud. I'm going to write down most of what I say, but not all. Please, please feel free to stop me when I do something that looks like magic to you. And I'll back up and be careful about the symbols that I write and the words that I say. Okay, so I have in my mind that I'm going to prove this thing inductively. I've got this theorem. Without thinking, I look at the theorem that I'm proving. I find the if statement, and I replicate the setup. So I'm going to say, consider an arbitrary binary tree. I need a label for this tree because I'm going to be arguing about it. T. Implemented as on previous page. And let n denote its size, the number of elements it contains. Okay, and I'm going to say that like this. The size of T is n. Okay, I'm going to use that shorthand here. All right, so this is the setup, and it means that I've got something to argue about. I'm going to make my argument about T. What does T look like? What does T look like? It's a binary tree, so it's either empty or it's not, right? So either T equals the empty tree, or T equals a root together with subtrees TL and TR. This corresponds to, the first one corresponds to what we typically call the base case. If T is empty, then we represent it how? How do we represent an empty tree? Just one null pointer, right? An empty tree is a null pointer. Then we represent it with one null, and the size of T is 0. So our hypothesis holds, because 1 is 0 plus 1. Okay? Any question about that? All right. So we're done with the base case. So now let's look at the inductive case. If T is not equal to null, then it looks like this. It's got a root together with subtrees TL and TR. They might be null, but we don't care about that. All we care about for the moment is T. For simplicity, we're going to label the size of TL and TR just so we have something to talk about. So the size of T is n. The size of TL, we're going to say, is A. And the size of TR, we're going to say, is B. Some of those might be 0. Doesn't matter. Okay? Then, by an inductive hypothesis that says for any smaller tree, that is, for any tree with j less than n elements, there are this many null pointers. How many is it? J plus 1, good. We know that TL has how many? How many null pointers in TL? A plus 1, that's right. So we set up this null hypothesis specifically so it can be applied to the subtrees. That's the whole point here. That's the whole point of the null hypothesis. So we know that TL has A plus 1 nulls, and TR has B plus 1 nulls. T, thus, has, how many nulls does T have then? A plus 1 plus B plus 1. Okay, are we done? What's that? The part I circled. What's the part I circled? Yeah, it's N. Look at this. Here's A, here's B, here's 1, right? Yes, A or B could be 0. I don't care, right? Fine, that's fine. We can handle that case. But A plus B plus 1 is N, or N plus 1 nulls. Yay. Some people say QED. I say yay. Okay. All right, any question about it? So, it is excruciating to stand up here and do a proof like this in talk aloud. The only thing I can imagine that's more excruciating is having to listen to it. So, what I'd like to know from you is, if I turned off the projector, could you recreate it? What do you think? If I turned off the projector, could you recreate the proof or something close? Okay. All right. The last thing I want to say about this proof is there are several different ways of proving this particular result. I chose the one that exploits the recursive description of the tree itself most directly. So, and because we're going to see proofs kind of like this on other structures in the class. So I chose the one that I felt like was the cutest, kind of, in that sense. All right, any questions about it? Is it okay? All right, I'm going to flip the slide here. All right, so we now believe that our implementation is okay. It doesn't have too many. It keeps track of our data. We know how to get around in it because we know how to follow pointers. But now I want to get back to the idea of the tree itself as a structure. Now here's how I want to talk about this. Well, okay, wait. So this tree contains data, right? And if we can't see what data our tree contains, it's nothing to us. It's pretty much worthless to us. So we need a mechanism for getting around in the tree in such a way that we can get our data out. Now, here's what I want you to do. I want you to imagine your friend that is going to school at some other university, okay? And who is not a CS major or a tech major. Okay, everybody got one of those friends? And now what I want you to do is text to them the contents of that tree. Okay, now what I want you to do for me is write down the data in the order that you would text it to them. Okay, so you have to communicate to your friend somewhere else the data in that tree. I want you to write down what order you'd put that data in the text. I apparently got tired of walking around. I found my perch. Okay, anybody want to offer their suggestion for what I'm asking you about your text messages? Anybody want to suggest it? Yeah? What order would you communicate this tree, the data in this tree? Plus, minus, slash, B, C, asterisk, D, E. Okay. Okay. I have a special name. Your traversal that you gave is a special one, okay? I'm not going to tell you what that name is yet. Secret name. Did anybody else write them down in a different order? Yeah? Tell me yours. You have to yell. B multiplied E. I think yours has a special name too. Secret name. 2. Okay, anybody else have a different order? Yeah? Okay. Okay. Asterisk. Slash. Okay. All right. Yours is called, ooh, yours has a secret name too, and I'm going to tell you what your secret name is. Ooh. His is called a level order because he went level by level reporting them. Okay? Anybody else have a different one besides these? Yeah? Minus. Okay. Okay. Yeah, okay. Anybody else have a different one? Anybody else have a different one? Yeah? Okay. BC slash, yeah, star plus. Ah, okay, that one has a special secret name too. Okay, fine. Anybody else have another one? How many of these are there? A lot is right. You can tell me exactly how many. Yeah, n factorial in general. So in this case, yeah, 8 factorial of them. All of the orders in which we can report these things are valid traversals. The only goal of the traversal is to get the data out. Now, it's nice if you have a principled approach to this. That is, it's nice if you can take any tree that I give you, even gigantic ones, and apply your mechanism for getting your data out. But it is not true that these secret ones are special in any particular way other than they happen to be ones that have flowed through our culture. In fact, you could take the reverse of each of those and it would be equally valid, but it just wouldn't happen to be, it wouldn't happen to fit the algorithms that we're going to talk about. And I'll talk about a little bit more about that later. In addition, those aren't even the only ones. I've got one for you. I've got a traversal for you. Okay? It goes like this. E, D, star, C, B slash plus minus. You know what I did there? I drew these lines. I tilted, this is the tilt it on its side and do level order. Okay? This is the do a scan line from here and tell them to me. If I can do this algorithmically, if I can do this on any graph, and any tree that you give me, golden. I'm golden. This will work. It's a traversal. It's a valid traversal. Okay? All right, yeah? Not in my algorithm. There is no shouldn't. I made this up. I'm making this up so that we could have this conversation. Yeah, right. This is the start at the bottom left-hand corner of the screen and go that way. Okay, traversal. It's valid. All right, any questions about this? So next time, we're going to spend some time on these secret ones. Then the time after that, we're going to talk about the level order. And, well, that's sort of where it goes from here. Happy Friday.